In the late 1950s, Margaret Burbidge elucidated the mechanisms by which stars convert simple elements into heavier ones, a process termed nucleosynthesis. Elements with fewer protons are more readily fused due to reduced repulsive forces that must be surmounted. The smallest element is hydrogen, possessing a nuclear charge and mass of merely 1. This achievement requires exceedingly high temperatures. Hydrogen must undergo fusion at around 15 million K. The fusion of hydrogen nuclei results in helium with a nuclear mass of 4. Due to its greater density, helium descends to the star's core, resulting in hydrogen creating a substantial layer above it, akin to the egg white encasing the yolk. Hydrogen fusion persists in a shell surrounding the helium core, maintaining the star's luminosity at previous levels. The subsequent events are dictated by the star's initial mass, and as will be demonstrated, the destinies of stars with varying masses diverge markedly. In the Sun, the temperature and pressure within the newly formed helium core escalate until, at 100 million K, helium initiates fusion to produce carbon. The denser carbon descends beneath the helium towards the star's core, where pressure and temperature persistently escalate. At this juncture, the Sun's external appearance will significantly transform. The Sun's mass expands and cools, increasing to over 90 times its main sequence size and consuming the planets Mercury and Venus. As the Sun expands, it becomes more luminous. However, the cooling of its outer atmosphere results in a reddish hue, signifying its transformation into a red giant. On the HR diagram, it transitions from the main sequence to the upper right quadrant. Simultaneously, the star's heated, compact core persists in the depths. A star with fewer than 8 solar masses will evolve into a red giant. The ongoing emission of subatomic particles known as neutrinos cools these stars, inhibiting their ability to achieve the temperatures required for carbon-oxygen fusion. These peculiar particles traverse from the core outward through the star without engaging with matter that possesses energy. A fragile envelope of hydrogen and helium encases the current carbon and oxygen-dense core. Stars from 8 to 10 solar masses possess adequate mass to produce the temperatures and pressures required to convert carbon into oxygen, neon, and magnesium. After a duration contingent upon its initial mass, the star resembles an onion, exhibiting concentric layers of progressively denser elements, ranging from the outermost hydrogen to helium, carbon, and, ultimately, the core. However, more is needed to extend the star's lifespan. Eventually, it depletes its nuclear fuel. Radiation pressure from the core gradually expels the gas shell for hundreds of years. The softly illuminated shell evolves into a planetary nebula, exposing the core at its center, now referred to as a white dwarf star, a gradually cooling remnant approximately the size of Earth. From an external perspective, the star seems to elevate in temperature. However, due to its diminutive size relative to main sequence stars, its luminosity diminishes. On the HR diagram, the star transitions from the red giant region in the upper right to a position lower and to the left. The track traverses the main sequence and concludes in the lower left of the HR diagram, enduring for billions of years while it gradually cools and diminishes from the stellar domain. The destiny of more massive stars holds greater significance in the narrative of pulsars. If a star's initial mass exceeds 10 solar masses, it can produce adequate pressure and temperature to sustain the fusion of progressively heavier elements. In doing so, it radiates significantly more luminosity in space than its low-mass counterparts, and at a considerably accelerated rate. The star's increased mass generates greater gravitational pressure at the core, leading to an intense rate of nucleosynthesis. A star with solar mass has a lifespan of roughly 8 billion years, while a massive star endures for about 100 million years. A massive star incessantly synthesizes heavier elements throughout its brief existence, accumulating them sequentially in its core. The denser elements descend to the core, while successive strata of less dense elements encase it akin to the layers of an onion. The accumulation of iron in the core results in its failure. The fusion of iron nuclei necessitates energy rather than releasing it. Thus far, the amalgamation of lighter elements into heavier counterparts has served as an energy source for the star, maintaining its expansion against the relentless force of gravity. However, gravity, the most feeble yet most expansive of all forces in the universe, ultimately prevails. Having exhausted its nuclear fuel, the star lacks the means to maintain its inflation against gravitational collapse. The nuclear fusion processes that sustained its brief existence have now ceased. Most of the star's outer layers implode within a brief interval, accelerating towards the core. There, they collide in a colossal impact so intense that they immediately create elements denser than iron that constitute our known worlds. The significant implosion leads to a core bounce. The amalgamation of matter surrounding the core during the collapse emits substantial energy. The star detonates spectacularly, dispersing the newly synthesized elements in all directions. The eruption radiates with the luminosity of 100 billion stars. It has transformed into a supernova. For a brief period, it surpasses the entirety of the galaxy. While the star's outer layers expand into space, the stellar core persists in its collapse. Without radiation pressure, gravity predominates and compresses the core to extraordinary densities. A peculiar object emerges from a massive star's demise. It emits a brilliant glow and rotates at an extraordinary velocity, possessing such density that it distorts spacetime and emits intense beams of radio waves into space. In January 1932, the husband and wife duo, Frédéric and Irène Joliot-Curie, published a paper in the Comptes Rendus Journal of the French Academy of Sciences, read by the young British researcher James Chadwick. In that paper, they detailed the bombardment of a fragment of the grey, toxic metal beryllium with alpha particles emitted from a sample of the radioactive element polonium. The experiment yielded a highly energetic but intangible form of radiation. While they could not directly detect the radiation, they could identify protons ejected from various materials positioned in the radiation's trajectory. They were perplexed that this novel type of radiation penetrated nearly all substances more effortlessly than any previously observed form. Previous experiments conducted by Walter Bothe and his student Herbert Becker in Germany demonstrated that the radiation could penetrate 200 millimeters of lead. This is remarkable, considering that less than 1 millimeter of lead is necessary to obstruct the most powerful energy known then, gamma rays. This novel radiation was so intense that its nuclear origin was difficult to contest. Both teams presumed that the unidentified radiation was a more energetic variant of gamma rays. If it could displace electrons from metals, why could it not also dislodge protons from the nuclei of other substances? However, this constituted merely a portion of the narrative. Chadwick was aware of the remainder. He was cognizant of their findings, yet he had not recognized them. Motivated by urgency, he replicated and expanded the experiments and confirmed the existence of the atom's third component, the neutron, within 3 weeks of rigorous investigation. The discovery was poised to yield significant ramifications for occurrences in the cosmos and on Earth. James Chadwick was born in Manchester, England, on October 20th, 1891. After graduating from the Honours School of Physics in 1911, he dedicated 2 years to working under the New Zealander Ernest Rutherford at the Physical Laboratory of Manchester University. Due to financial difficulties, Chadwick relocated to Berlin to pursue studies at the Physikalisch-Technische Reichsanstalt in Charlottenburg under Professor Hans Geiger, renowned for the Geiger counter. In the subsequent year, conflict erupted. Thomas Cook, the travel company, informed British citizens that they faced no imminent threat and thus had no necessity to evacuate Germany. However, Chadwick was soon apprehended as a civilian prisoner of war in the abandoned stables of a racetrack at Zivilgefangenenlager, Ruhleben, where he remained for the subsequent 4 years. They prohibited him from conducting experiments, but permitted him to read and engage in discussions with other physicists. Chadwick undertook minimal research despite the oppressive circumstances, utilizing a widely marketed toothpaste by Berlin Auer during that period. The toothpaste contained thorium to enhance tooth brightness. Utilized toothpaste containing thorium. Possess radiant, luminous teeth. An extraordinary brilliance. Upon the war's conclusion, Chadwick returned to Manchester, where he collaborated again with Rutherford on the transmutation of elements, converting one element into another. For centuries, alchemists endeavored to achieve this feat, but were completely unsuccessful. Eddington proposed that stars could achieve what alchemists could not. Now, Rutherford sought to understand the mechanism. After the 19th century, Rutherford conducted experiments that demonstrated the presence of the atom's nucleus. He illustrated that although most particles traversed the gold foil directly, some were deflected back. Rutherford famously stated it was as if you fired a 15-inch naval shell at a piece of tissue paper, and the shell returned to strike you. This experiment led Rutherford to conclude that the atom predominantly comprised a ghostly cloud of electrons encircling a small, dense, impenetrable nucleus. What about the nucleus? What materials comprised it? At that time, two particles were recognized: the negatively charged electron and the positively charged proton, with protons being the more massive. The issue was that the masses of various elements did not correspond. A hydrogen nucleus possesses a charge of +1 and a mass equivalent to a proton. Conversely, a helium nucleus possessed a +2 charge and was 4 times more massive than a hydrogen nucleus. 4 protons in the nucleus, +4, and 2 electrons were required to balance the electrical charge, resulting in this mass. Although electrons possess mass, scientists considered them sufficiently light relative to protons, and their contribution to overall mass was negligible for the problems addressed. Nonetheless, this model exhibited an additional issue. In 1925, Dutch scientists George Uhlenbeck and Samuel Goudsmit discovered a fundamental property of nuclei, protons, and electrons known as spin, whereby each particle possesses a spin of either +1 to 2 or 1 to 2, with no intermediate values. The sum of the particle spins of an odd number of particles will yield a half-integer result, such as 1 to 2 or 3 to 2. Upon measuring the total spin of a nitrogen nucleus, we found it to be a whole number despite comprising 21 particles, 14 protons, and 7 electrons, which neutralized the positive charge of the 7 protons by Rutherford's theory. A third type of particle must exist within the atom that does not affect its charge, but contributes to its mass equivalent to that of a proton. Rutherford hypothesized that this substantial neutral particle must amalgamate the massive proton and the lightweight electron, allowing nuclei to possess the observed masses. In his Beckerian lecture to the Royal Society in 1920, Rutherford elucidated that it may be feasible for an electron to associate more intimately with the hydrogen nucleus, resulting in a form of neutral doublet. Rutherford designated this theoretical particle as the neutron. Rutherford and his students dedicated the subsequent 12 years to pursuing the neutron, but have yet to succeed. In 1964, Chadwick remarked that certain attempts were so desperate, so far-fetched, as to belong to the days of alchemy. However, upon reading the Joliot-Curie paper, he realized he was on the verge of discovering this elusive particle. As mentioned at the beginning of this chapter, the Joliot-Curies proposed that the penetrating radiation comprised gamma rays. Chadwick dismissed this explanation, noting that gamma rays lacked sufficient energy to generate the observed outcomes, as they could not dislodge protons from the various materials tested at the recorded velocities. By the time the Joliot-Curies reconsidered their position 3 weeks post-publication of their results, Chadwick had already triumphed. Chadwick allocated limited time to establish a replica of the Joliot-Curie experiment. Chadwick persisted late into the night, disregarding Rutherford's mandate prohibiting laboratory work after 6 p.m., as he was reluctant to squander time or jeopardize his sensitive experimental apparatus due to potential disruptions from other researchers. Chadwick utilized polonium as a source of alpha particles. He positioned a beryllium sample before it, from which enigmatic penetrating rays radiated. He positioned targets of diverse types along the trajectory of these rays: hydrogen, helium, lithium, beryllium, carbon, air, and argon. Chadwick subsequently positioned a detector before the samples to identify any emitted particles. The unidentified radiation displaced protons from the samples, which he subsequently detected. Chadwick demonstrated that gamma rays lacked sufficient energy to dislodge particles from the samples by measuring their velocity. The penetrating radiation necessitated particles possessing a mass comparable to that of a proton, yet devoid of any electrical charge. In a correspondence to the journal Nature dated February 27, 1932, he stated, "The difficulties vanish, however, if one posits that the radiation comprises particles with a mass of 1 and a charge of 0, or neutrons." Fatigued, yet invigorated, Chadwick proclaimed his discovery at a casual assembly of physicists called the Kapitsa Club. The attendees responded with enthusiasm and recognized the significance of the discovery. In a comprehensive report of his experiment published in the Proceedings of the Royal Society, Chadwick articulated his discovery with caution. "It is evident that we must either abandon the application of the conservation of energy and momentum in these collisions, or adopt an alternative hypothesis regarding the nature of the radiation. The law of energy conservation, that energy cannot be created or destroyed, is widely accepted." In 1932, there remained a debate regarding the applicability of the same conservation laws in the quantum realm as in the macroscopic realm. Chadwick asserted, "If we assume that the radiation is not quantum but comprises particles with a mass nearly equivalent to that of the proton, all the challenges associated with collisions vanish, including those regarding their frequency and the energy transfer to various masses. To elucidate the significant penetrating capability of the radiation, we must additionally posit that the particle possesses no net charge. The particle may represent a close amalgamation of a proton and an electron, akin to the neutron Rutherford addressed in his 1920 Beckerian lecture. What is the status of the Joliot-Curies? Frederick was understandably disheartened by being preempted by Chadwick, and privately articulated his frustration regarding the necessity of publishing scientific evidence to establish precedents while observing other researchers capitalize on that published work. This was the catalyst for Chadwick's success. Nevertheless, a magnanimous Frederick publicly acknowledged Chadwick for the discovery. Electrically neutral neutrons are entirely impervious to the positive repulsive force exerted by protons within an atomic nucleus. Consequently, they possess an extraordinary capacity to infiltrate the nuclei of other atoms. In early 1939, Otto Hahn, conducting research in Berlin, demonstrated that the uranium nucleus undergoes fission when subjected to neutron bombardment, releasing substantial quantities of energy. 2 months later, the Joliot-Curies published a letter in Nature declaring that the uranium nucleus not only underwent fission but also emitted additional neutrons, which would penetrate and further split additional uranium nuclei, thereby releasing even more energy. Some perceived the emergence of a chain reaction as exhilarating, whereas others regarded the ramifications as alarming. Physicists from both camps recognized that the Joliot-Curie findings indicated a method for unleashing vast quantities of energy with alarming consequences for weaponry technology. They had established the groundwork for the world's inaugural atomic bomb. Several years later, they would employ the same scientific principles that had unveiled the essence of the stars to obliterate hundreds of thousands of lives and subject the remainder of humanity to a perpetual threat of extinction. During this period, an exceptional young Indian scientist traveled from India to England to study under Eddington.